All right, hello, welcome to Math 2414. This is going to be our first week, and this week we're going to go ahead and cover 3D coordinate systems as well as start introducing vectors. All right, so now let's actually go ahead and get started with our 3D coordinates. So I want to start off with is start comparing some terminologies and just some different aspects between 2D coordinate systems and 3D coordinate systems. So first of all, one thing that's a difference is that in 2D coordinates, we have what are called ordered pairs, which kind of tell us a point along in that area. They kind of give us our directions. And that's usually written in the form of some number A, comma, some number B. Meanwhile, in 3D, since we're going from 2 to 3, we're going from ordered pairs to ordered triples. And these, of course, are going to be written in the form A, B, and that's a comma, C. Now, those tell us directions, but they tell us directions in what? So when we think about 2D, we are looking into planes. Because we only have two axes. We have our X and Y axes. Like this. It can only lie, like our points in 2D can only lie along these planes, within this plane. Whereas 3D tells us more about space in general. In here, we have an x-axis going one way, a y-axis which is perpendicular to that, and we have a z-axis which is perpendicular to both of those. So we have an x, our y, and our z. And even within this, we have different coordinate planes. So, for example, we could stay only along our xz axis and we can stay only along our xz axis and not worry about anything involving y. We can stay along our xy plane and not worry anything about z, or we can stay along zy and not worry about x. So now that we've kind of established some of the main differences between 2D and 3D, let's go ahead and just do a quick review on how to draw points in 3D. So your first step you're going to do is go ahead and draw your axes. So what I would do is, I normally start with your X kind of going this way, your Y kind of going this way, and then your Z is usually going to go up and down. And then just kind of draw a little bit like that, just to kind of indicate the negative space. So now let's say we want to graph the points. Let's say we're going to graph the point 3, 3, 3. Pretty easy point. So what we're going to do first is to draw our x value. First, we're going to go ahead and move 3 units along our x direction. So we start here, 1, 2, 3. Then what we're going to do is we're going to start moving along our y-axis, which we see is kind of going perpendicular to that. So 1, 2, 3. And let me just go ahead and show the points here just so we can kind of get an idea of where we are landing at. And then from here, we have to go ahead and move 3 units up from this point. So just straight up, so 1, 2, 3. So while it looks kind of wonky, if you kind of visualize it in 3D, you're just kind of going out and back up. It just kind of looks a little weird since we're having to, of course, look at this in a 2D space. And then this kind of brings us back to, so now this kind of brings us to the concept of projections. So projections are kind of essentially whenever you kind of move an already established point onto like a different part of the plane, of like onto a different part in space, usually along some sort of plane or line. So let me go ahead and define, like kind of show like just a kind of general overview of how to project points. And then I'll kind of show you visually as well as how this kind of works. So how to project just is kind of like so we're going to go ahead and do this and just kind of show you how to do this algebraically, then I'll show you visually kind of how and why it works. So we have our three main coordinate planes. We have our XY plane, our YZ plane, and our XZ plane. So when our XY plane, so of course we have our normal point, we're going to call our normal point ABC. If we want to project ABC onto the XY plane, we can think of it as if we're on our XY plane, that means Z equals 0. So, but we can leave our A and B alone. So just be A, B, 0. Similarly, with our XZ plane, that means our X has to be 0. So we're going to be at 0, B, C. Like all we're changing is just that one point. And we're changing that to 0. So lastly, for our XZ plane, it's of course going to be A, 0, C. But now we have our planes. Those are kind of easy enough. And then now let's think about, because occasionally you'll get a question like this, it's going to be how to project onto an axis. So if we're looking at our x-axis, we can think about our x-axis. We know that there's an x, so in a 2D coordinate, we know our x-axis is when y equals 0. This is the same thing in 3D, but your z is equal to 0 as well. The only point that is defined is your x. So it would just be A, 0, 0. With your y-axis, it's the same concept. The only thing that is not at 0 is going to be your y. So 0, B, 0. And then, of course, your z is going to be at 0, 0, C. So let me go ahead and draw this out and kind of show you sort of how it works. So let's say once again, we're going to have a point in 3D. I'm going to go ahead and mark our point as being, let's just say right here. So now we have to think about, almost kind of think backwards to what we did earlier when we drew our plane. So we know we have to be some distance away from our x-axis. Or well, okay, first of all, go back with our z. We have to be some distance down, like let's say and in this case, we are in the first octant. In this example, we are in the first octant, so A, B, and C are all positive. So let's say we are some distance up off the z-axis. So now let's kind of move back down, and now let's say we're now at the xy plane. And then now we also know we are also some distance away. Now that we're back down from the xy plane, we can get our way back to our original x and our initial y. But from each of these, we can kind of move everything together and actually end up creating a box. Because we can, in a way, treat our point as sort of being a diagonal of like some sort of rectangle between the origin and that point is just the diagonal of a rectangular prism. So now if we think about this, we actually now have a box. And when we think of projecting, you're almost kind of sliding this point around your edges of this box in order to get where you need to be. So like for example, if we're wanting to project down to our xy plane, we go ahead and just move this point just straight down to where our z is 0. Now let's say we want to project onto the x-axis. Well, we can still move down and then move back over to where our x-axis is, and then now this point is our projection onto the x-axis. So if you think about it, you're just kind of just sliding things over. That's essentially what mainly projecting is, just kind of just sliding things over until you kind of get to where you need to be. And also another thing is, so earlier we mentioned how this makes a rectangular prism. Well, that kind of helps define like what exactly we're doing. So essentially all of this ABC, that's essentially graphing within a 3D rectangular coordinate system. So now that we've kind of mentioned a little things about how points and our axes and like our coordinate planes work, let's kind of move on and so a little bit more abstract into this. So let's go ahead and think about another. So we kind of mentioned earlier within 2D and 3D, we were talking about our differences. Well, in 2D, there's another really important one. So when we're thinking about graphing in 2D, we only have two axes. So really, all we can really do is we can just define points anywhere in here, or we can create a line. That's all we can really do. We can't really go, but we have to stay within that 2D plane. So we can either have individual points or we can have lines. That is all we can do. And for 2D, or what we also call r squared is also what we can call 2D. In 3D, however, we can have dots, of course. We can have dots, we can have lines, but what we can also do is we can actually go ahead and 3D/R cubes, we can also create surfaces. because now we have that extra axis to where we can go ahead and do things. So that brings us, so let's go ahead and actually define what a surface is. A surface is actually a very broad definition. A surface is essentially just an equation involving x, y, and z in r cubed, or our 3D space. Now, the most important part of this definition is r cubed, because because essentially x, y, and z can be 0. If they're in the 0, they may not be in the equation. They exist on the surface, but they may not actually technically be defined in the equation. The important thing that really defines a surface is that it is in 3D space. Because you cannot have a surface in a 2D space. So now let's go ahead and kind of go over how to start graphing some surfaces. We'll do a quick review of that. So graphing surfaces. So let's go ahead and do this through some examples. In this example, we want to graph z equals 2 in r cubed. Now, it's z, so that's usually let me go ahead and do this and so it's exactly the same. That's z, that's 2. All right, so normally with the z, that's kind of implied that you're in r cubed. So we'll go over as to why it's kind of important to know which space you're in and the context in another example right after this one. So first of all, we're going to go ahead, similar to our points, we're going to go ahead and graph our axes. And then we know that, of course, our z has to be equal to 2. So we're going to go up 1, 2. The thing is that with our z equals 2, if we have a z equals, so if we have a z equals 2, that's all we have. There is nothing defining what x and y can be. X and y can be anything. X can be 1/2 or like 4 million. It doesn't matter. Y can be a similar way. Y can be like -3 or like 400. It doesn't really matter. It just has to exist along any point where z is equal to 2. So what we can do is we can actually go ahead and draw this out. We can draw out and say that if we can go ahead and move in this direction, we can move out as far as we want in our x and y directions. And that is still valid just as long as we stay at that within that z equals 2. So what we can do is if we draw this out with all those potential points, we essentially get a plane. So if we wanted to describe this in words, we can say this is just an infinite plane, since there are no bounds in our x and y direction, parallel to our xy plane, going through the point, just to give us a reference, zero, 0, 2. So now let's go ahead and move on and do another example. In this example, we want to graph x equals 5. Now, unlike z, x can still exist in 2D. So let's go ahead and just write an R3 right here and an R2 right here. So if we're graphing it in 2 dimensions, x equals 5 is a pretty simple graph. It's just that line at x equals 5. But of course, if we graph it in 3D, we are going to get something pretty different. So we can move on and go to our x equals 5. We can go up. We can go up and down. We can go move to the side, but we cannot go forwards or backwards on that plane in relation to our x-axis. So therefore, we get a plane So therefore, we just get a plane. So we can say this one is just a line. That one is just a vertical line going through the point 5, 0. Whereas here we get an infinite vertical plane parallel to the YZ plane going through the point 5, 0, 0. So as you can see right here, knowing the context for some of this is really important. In 2414, we will typically stay within our 2D XY coordinate systems. You're not really going to have to worry about this too much unless you take 2415 like next semester, because that one deals a lot with 2 and 3D. This, other than like the next couple sections, we mainly just stay within 2D. And then I just want to do one more example that isn't quite as obvious on how to graph it. And then we will go ahead and do a couple quick definitions, and then we should be getting fairly close to starting our next section. So for our next example for graphing, I just want to do a quick one. We're not going to deal with defining anything. We just want to be able to draw it. So our example this time is going to be y equals 2x. So first of all, what we need to do is we always start off and we draw our axes. So now let's think about this. This one's a little different since this time we're defining not just one, but two. So if you're drawing in 3D and you have something that isn't quite as obvious to come by, one thing you can do is you can actually try to start drawing, if you can, draw it in 2D. In this case, it's pretty easy. If you only have, 2 variables, you can go ahead and move this to 2D. So where we have our x-axis and our y-axis, and we can draw and y equals 2x is a pretty easy graph. Just kind of go up kind of steep like that, you're good. Now, if we kind of can visualize this in 2D, what we can do is we can actually move this down to our 3D. So of course we have our z, our x, and our y down here. And usually it helps to also kind of put in some points that may fit within the equation. So we know 0, 0 will fit within the equation. We can go and do 1, 2, so 1 over, 2 up, or 1 over, 2 to the side, and keep going like that, and we can draw our little line. So we have our line drawn like that, but now we have to think, so now we kind of have our 2D graph sketched out. However, once again, we have to think about now we are in 3D. So if we look at our equation, we see there's no z, so therefore z is undefined. What we can do is we can just draw a plane going straight up and down, but it has to be along this line. So that's just a little neat tip. That's just a little tip if you're having trouble drawing. Try drawing different graphs in 2D, try drawing different points, and then just kind of put it all together, and then just kind of put it all together at the very end. A quick little thing that I want to just do a quick bit of clarification on, just as a quick reminder. We have just been working with surfaces, which is different from solids. I remember when I took this course, they were very big on surface versus solid, so I just wanted to do a quick little, I'm not really going to do a ton of work with them, but just quick little shout out. Surfaces, they're going to be equations with an equal sign. Solids are going to be inequalities. And then those, of course, are going to have some sort of less than or equal to, something like that, something in that vein. So I just wanted to give that a quick little shout out. So for example, if we had x squared plus 2y plus 3z equals 0, that would be a surface. If we had x squared plus 2y plus 3z equals 0, that would be a solid. So in this case, I don't know exactly what this graph looks like, but this would just be, let's just say this is just some sort of plane, and that's all we have here. This would be a brick. Wait, this is a less than. Here we have the same plane, but instead of just shading up here, we shade everything down here as well. Like I said, we just get a solid brick. So that was just my quick little reminder on that. So now let's go ahead and move on to just some other little fun things with 3D. So first of all, let's go ahead and go over our distance formula. So back in like all your previous stuff, whenever we worked in 2D, we knew our distance between, let's say, our distance between point 1 and point 2 was equal to x2 minus x1 squared plus y2 minus y1 squared, all that square rooted. Well, luckily when we move to 3D, it's actually a very, very simple change. In 3D, our distance is now x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. All under a radical. Only differences is now we have our little friend z. We don't have to do any other adjustments. There is a proof in the book showing why this works, but I will not be going over that right now. But going from our distance formula, this actually brings us to something kind of interesting. So if we kind of rearrange this one in r, oh, that's r cubed. If we rearrange this one, we can go ahead and say, of course, that the distance between our 2 points squared is equal to all that, x1 minus x2 minus x1 squared dot dot dot. I don't want to copy all that down. But that brings us something kind of interesting. So if we have a sphere, so if we think about it, a sphere is something in 3D that has a constant radius from the center. That never changes. No matter where we go, that formula never changes. So what we're going to go ahead and do is actually go ahead and we can kind of rearrange this formula to actually give us a formula for a sphere in 3D, in 3D coordinates. So our formula for a sphere is x minus h squared plus y minus k squared plus z minus l squared equals r squared, where HKL is our center and r is our radius. So I just want to do, we have a few minutes. I want to go ahead and do a quick example on just with spheres. So in this example, we are going to prove this equation is a sphere and find the center and the radius. So in this equation that we're going to use is going to be 2x squared plus 2y squared plus 2z squared equals 8x minus 24z plus 1. So in our sphere equation, we know that all of our x, y's, and z's are on one side and all of our constants are on the other side. So we're going to go ahead and move the 8x and the 24z to the other side to give us minus 8x minus 8x. Actually, those don't cancel. I miswrote that. 2x squared minus 8x plus 2y squared plus 2z squared minus 24z equals 1. So we're getting closer, but there's one thing we can go ahead that we need to take care of first, and that is actually factoring out a 2 and moving it to the other side. So what we can do is we can pull out a 2 and say we have x squared minus 4x plus y squared plus z squared minus 12z equals 1. So we can just go ahead and move this to be 1/2. So now we're getting a lot closer. So now what we can do is now we can go ahead and look at our individual pieces just to finish this sphere equation. So let's go ahead and combine our x's, our y's, and our z's. So now we're getting really close. So our y is fine. We don't have to worry about it. It's just our x and our z. So we're not quite in our form to where we can go ahead and say we have x minus h squared or z minus l squared. But what we can do is we can go ahead and just complete the square for both of these. So we can go ahead and get x squared minus 4x plus 4 plus y squared plus z squared minus 12z plus 36 equals 1/2 plus 4 plus 36. Now we can go ahead and combine everything to get us x minus 2 squared plus y squared plus z minus 6 squared equals 40.5. I apologize, my handwriting's sloppy. I have not done this in a couple months. So our center of so looking back at our formula, we can see that our center is going to be at 2, 0, 6. Oh wait, give me just a second. This isn't going to affect anything. That's a plus. These are all pluses right here. That does not affect anything though. So 2, 0, negative 6. And our radius is going to be the square root of 40.5. So that was a quick little sphere problem. Vectors. So now we're going to go and start moving into vectors, and this is going to, especially if you're taking physics, this is going to be really, really important later on. And of course, if you take 2415, this is kind of the basis of that course. So let's go ahead and first define what a vector is. So our vector is a quantity with magnitude and direction. So, for example, if you say go west, that's not a vector because we don't have a definite, we don't know how far. If you say go 30 miles an hour, that's great, like but that's not a vector. That is just a quantity with magnitude, or what we call a scalar. But if you say go 30 miles an hour west, that gives us a vector, since that gives us a magnitude and a direction. So now let's go ahead and first of all kind of show what a vector is. So typically vectors are we typically visualize them as being, we have a little point right here, and goes out and we have an arrow. So our length, so from here to here, that length is essentially our magnitude. And then the direction this arrow points, yeah, that's our direction. The arrow shows it. Yeah, the arrow shows us our direction. And if we're talking about vectors, we either write them either bolded, like we just have our letter that defines them. Our name is either going to be bolded, or we're going to go ahead and just draw an arrow on top of it. So vectors, they can just exist in a point, or they can just exist like this, or we can go ahead and think about it as being as like a displacement from where you're going from point A to point B. So if we're thinking about displacement, or from A to B, we have to have an initial point and our terminal point. So our initial point, whenever we have a vector, is going to actually be the tip right here. So that is going to be our initial. And then our terminal shows us where we're going, which is going to be our tail or the arrow. And if we want to go ahead and if we're talking about displacement vectors, we usually write them in the form AB with an arrow on top. All right, so now let's think about vector addition, since this actually does come up a lot when you're talking about displacement. So vector addition, technically in the book, you know, it has a really long definition. It's essentially if you have two vectors, u and v, they're positioned so that the initial point of v, let me just go ahead and draw this out. So if you have vector u, w and v are vectors positioned so that the initial point of v is at the terminal point of u, then the sum of u plus v is going to be from the initial point of u to the terminal point of v. So therefore we get u plus v. And we also typically tend to call this the triangle law, just because we have because this is it's two initial vectors, and that third side create two vectors added, that third side creates a triangle between them. And we also have what is called the Parallelogram Wall, which essentially is the same thing, except it also shows that you can start with v first and then go to u. You can do v plus u, and that is the same thing as saying u plus v. So now our next little the next thing we can also do with vectors is we can actually multiply them by a scalar. So let's say we have a vector. If we have a vector, let's say we can multiply it times a scalar to make it stay in the same direction but increase the magnitude. Or you can go exactly the opposite direction, but it can't be like, it has to be a full 180 degrees. You cannot go from here to here. You can't do that. So, and of course, and also, these are all, whenever you do a scalar, all produce parallel vectors, which essentially means that they have the same or exact opposite direction. And it does not matter if, and magnitude doesn't matter, just as all we worry about is the direction when it comes to parallel. So let's go ahead and actually kind of show how scalar multiplication works and kind of give it more of a hard definition. So essentially, let's say we have some value c, which is a scalar, and then we have a vector v, then essentially we're saying that if we do cv, which is called a scalar multiplier, c is a scalar multiplier, that cv is essentially the vector whose length is c times as long as our initial v and has the same direction if c is positive, or exact opposite if c is negative. So essentially, let's say we have our vector v is this. If we said, let's say we had 1/2 v is the same thing with just half the length. 3v has a much longer length. And then if we had negative v, that is going to be the same magnitude, just opposite direction. So that actually brings us to vector subtraction. So if, let's say, we want to subtract vector u and vector v, we don't really know how to do that just yet. We don't really have a good way to do it, but similarly, if we're just adding or subtracting two numbers, what we can do is we can actually go ahead and just say that we're going to go ahead and add a negative. So we can say that u minus v is the same as u plus negative v. So if we have a negative v, that's essentially saying that's vector v just flipped the opposite direction. So let's say, so this is a bit easier if we go ahead and kind of draw this out. Let's say we have vector u like this and vector v like this. If we wanted to do u plus v, that would just essentially be going over, going straight up, and our resultant is going to be from here to here. But now let's think about our u minus v. Well, like we said, that's really u plus negative v. So we draw u the same. But we draw v almost exactly the same, but just the opposite direction. So therefore, our resultant vector is actually this. So we've all kind of just been thinking about this just kind of visually, but not really algebraically. So that brings us to components. So essentially with components, those essentially break down the vector in terms of each kind of individual axis. So vectors can be in any amount of space, 3D, 2D, 4D, 5D, as much as you want. We only care about 2D and 3D right now. So when we think of components, we technically still have an initial point, but our initial point is going to be the origin. Whereas our terminal point is just going to be some point in space. And we're just going to go ahead and put this as coordinates like that. So, like we said earlier, when we think of displacement, we're essentially going from point A to point B. So, what we can do is say that our vector A, our displacement vector A, when we're moving from the origin, is equal to A1, A2, A3. Because what we can do is we think about this as saying that we have A1 minus 0, that's how much we moved in the x direction. A2 minus 0 is how we moved in the y. And then A3 minus 0 is how we move in the z. And we go ahead and we actually use these little pointy triangle brackets because that just helps us differentiate between coordinates and vectors when we write it out. But let's go ahead and think about what if our initial point is not at the origin? Let's say our initial point is going to be just at some x1, x2, x3. Let me rewrite that. It's been a long day. Our initial is at x1, y1, z1, and that's the regular point. And then our terminal is going to be x2, y2, z2. Once again, we're kind of thinking about how far did we move in each direction, so therefore, the way we would define this vector would be x2 minus x1 for your first number, y2 minus y1, and then z2 minus z1. So now that we kind of figured out how to break down our vectors into an algebraic and into like algebra essentially, we can actually now do more with it. So let's say we want to figure out how to find the magnitude of a vector. So we usually write magnitude as just saying, as putting either some pipe brackets around it or two pipe brackets. All right, whatever floats your boat. So there's two different ways we can solve it, but it just kind of depends on if you're in 2D or 3D. So if you are in 2D, it is just going to be, and vector A is equal to A1, A1, A2, or in 3D, A1, A2, A3. In 2D, our magnitude is going to be the square root of A1 squared plus A2 squared. And then in R3, it is going to be the square root of A1 squared plus A2 squared plus A3 squared. Pretty much the same reasoning. It's pretty much the same thing whenever we did distance between 2 points in 2D and 3D. So now that we've kind of done this, let's go ahead and go over some quick little properties, and then we'll go ahead and do some example problems So just some really important properties to remember. And I mean, a lot of these are kind of just common sense, but or basic algebra, but of course, A plus B is the same thing as B plus A. A plus B plus C is the same no matter how you bracket it off. It just has to go in that order. Then A plus 0 is A minus A is 0, or A plus negative A, whichever way you want to write it, same thing. If you have a scalar and addition, you can go ahead and just split it off. If you have two scalars, once again, you can break it down. And then lastly, 1 times A is just A. So yeah, just kind of remember those properties. I mean, like I said, most of those are kind of just common sense, but just in case, or like just in case you may need them for something, or like you're like overthinking them, you can just or overthinking a problem. I know I do that a lot. It's just nice to be able just to look back at that. So now some examples. So we're actually going to do like a little 4-parter. So for part 1, so for all of these are vectors. A is going to be -3, 4, and we're just going to work in 2D this time. And B is going to be 9, -1. So for part 1, we want to find a plus b. So pretty much now that we have these in component form, this is actually just going to be a lot easier to do. So what we can actually do is say we have negative 3, 4 plus 9, negative 1. And what we can do to make this a lot easier is just actually combine these as individual pieces. So we can say we have negative 3, 9 plus 9 plus 4 plus negative 1, which is going to simplify out to 6, 6, 3. So, and for these, you just kind of work piece by piece, just x's stay with x's, y's stay with y's, z's stay with z's. But you can just kind of work that way as in component form, which makes it a lot easier. So now we're going to do another example. So we're going to do 4a plus 2b. So first of all, what we can do is we can go ahead and do our scalars. So 4a is going to be negative 3 times 4 is negative 12, and then 4 times 4 is 16. 2b is going to be 18, negative 2. And then now we just have to add these up. So we can get negative 12, 16 plus 18, negative 2 is equal to 6, 14. For part 3, we want to just find the magnitude of a, which is just a simple plug and chug. So we know we moved 3 in the first direction, so 3 squared, or negative 3 squared. And then we moved 4 in the y direction. So 4 squared is just going to be square root of 9 plus 16, square root of 25, which is just 5. And then finally, for our last part for this, we want to actually find the magnitude of a minus b. So subtraction also now gets a lot easier, because what we can do is we can now say that, so similar to how we did a1 plus b1, we can now just do a1 minus b1, and then a2 minus b2. So that gives us negative 3 minus 9 is negative 12. 4 plus a negative 1. 4 minus a negative 1 is 5. And then we can just plug that in and plug that into our magnitude to get us negative 12 squared plus 5 squared. 144 plus 69 plus 25 is 169. So our magnitude is just 13. So now that we've kind of worked with some of our properties, let's go ahead and just touch on three special vectors. So these vectors are what we're going to call standard basis vectors. So in here, These are going to be called I, j, and k. I is going to be defined as essentially our x-axis, going 1 unit in the x-axis. So if we're in 3D, 1, 0, 0. In 2D, just 1, 0. J is similar, it's just we're going just 1 unit in the y. And then k is 1 unit in the z. So if we think back to our properties of scalar multiplication, let's say we have let's say we have a vector A, which is A1, A2, and A3. If we think back to scalar multiplication, so this is kind of based on the properties of addition and scalar multiplication. So first of all, what we can do is we can technically break this up into 3 vectors just based on our definitions of adding. So we can get A1, 0, 0, A2, 0, 0, A2, 0, and 0, 0, A3. Now we can go ahead and use properties of scalar multiplication and pull each one of these out to get us A1 times 1, 0, 0 plus A2 times 0, 1, 0. And then A3 times 0, 0, 1. Well, we have a 1, 0, 0, a 0, 1, 0, and a 0, 0, 1. So what we can do is we can actually go ahead and substitute these out to get us A1 to where we can now get A1i plus A2j plus A3k. So essentially we can write any vector in the form of ijk. So just essentially what would have been here just now goes in front of an I. What goes, your A2 just goes in front of a J, your A3 goes in front of a K. So now I just want to do a couple quick examples. In this one, we want to find this one. Let's do another one. Find the magnitude of A minus B, where A is 4i minus 3j plus 2k, and our B is 2i minus 4k. So now, first of all, what we need to do is figure out what our A minus B is. So our A minus B is going to be our A, so 4i minus 3j minus 2k, minus our B, 2i minus 4k. Go ahead and distribute the negative to get us 4i minus 3j minus 2k. Wait, that's a plus 2j. Plus 2k minus 2i plus 4k. Now we just combine our like terms. So we have a 4i and a minus 2i, which gives us a 2i. Our j is just by itself, so minus 3j. And we have a plus 2 and a plus 4k, so 6k. So that is our a minus b. So now what we need to do is find our magnitude of this. So our magnitude of a minus b is just going to be our square root of 2i of 2 squared, so 4, plus negative 3 squared, which is 9, plus 6 squared, which is 36, which gets us square root of 49, which gets us to 7. All right, so our unit vector. So now next thing I want to touch on is unit vectors. So our unit vector is just essentially a vector whose length is 1. So for example, even like those ones we know, I, j, and k are all unit vectors, but they don't have to just be along an axis. They can go in any direction. All they matter is that magnitude is 1. But if it's not on an axis, that makes things a little harder. So if, let's say, our vector A does not equal 0, the unit vector with the same direction as vector A is, or vector E is, or is what we're going to call our unit vector, is equal to 1 over the magnitude of A times A, or just vector A over divided by magnitude of A. So I want to go ahead and do a quick example. So for this one, it's going to be find the unit vector of 8, negative 1, 4. Just find the unit vector essentially with the same direction as 8, negative 1, 4. So what we need to do is first find our magnitude of that vector. So we know it's going to be 8 squared plus negative 1 squared plus 4 squared, which is equal to the square root of 64 plus 1 plus 16. That is equal to the square root of 81, which is 9. So what we just have to do now is just multiply 1/9. Use a scalar to multiply 1/9 times 8, negative 1, 4, which gives us 8/9, negative 1/9, and 4/9. All right, and then I'm going to go ahead just to kind of save us a few minutes. I'm going to leave y'all with the challenge problem for this. And this one is going to be find the vector with the same direction as 6, 2, 3 with length of 4. So what I want y'all to do is go ahead and try to solve, go ahead and pause, try to solve this on your own. And the answer is going to be 24 over 7, 8 over 7, and 12 over 7. So yeah, that's going to be the answer. Go ahead and try. So hopefully you guys have solved that all right. And I just want to go ahead and touch on something pretty quickly. So essentially, I kind of want to show how you can view how components and then angle and magnitude are related. So essentially, if we think about it, like we said earlier, our vector is essentially just kind of goes in a direction like this. And this is typically, and whenever we do this, we're typically just in 2D, not 3D. So let's say we know our, if we break it down to our components, we know it goes some amount over in the x direction and then some amount up in the y. Like we can break this up into a right triangle. So if you have your angle and magnitude and you want to go to components, what you're going to do is you're going to say that your x value is just going to, and then you have your theta. Your x is going to be, we're just going to call this our magnitude of A. Your x is just going to be your magnitude of A times the cosine of that angle in relation to the positive x-axis. And your y is going to be your magnitude times your sine of that theta. So now if you want to go ahead and go from components to angle and magnitude, that is pretty simple. So we've actually already gone over on how to find the magnitude, which is just going to essentially be the square root of x squared plus y squared. And then to find your direction, essentially you just have to know that tangent of theta is equal to your y over x. And then you can just solve for theta, and I don't think we have enough time to really do any sample problems with this, so that is all I have for today. Hopefully you enjoyed our first review session, and good luck on your quizzes and homework.